What's up guys, this is Masi, welcome to my channel. In this video I want to talk about quantitative changes in equilibrium systems, and this is part of chapter 7 from Chemistry 12 by Nelson, and this section is section 7.5. So let's start. Carbon dioxide gas can dissolve in liquid water, H2O, to form the solution of carbonic acid, which is H2CO3, in a reversible reaction. This equilibrium system is involved in maintaining the pH of your blood. If your blood pH falls outside a narrow range of values, for example lower than 7.35 or higher than 7.45, you can suffer life-threatening symptoms. Cellular respiration produces aqueous carbonic dioxide and liquid water. When these products are transferred from the cells to the blood, they can combine to produce aqueous carbonic acid, which lowers blood pH. The chemical reaction system can be represented by this equation, which is CO2 plus H2O gives you H2CO3. In critical cases of low blood pH, a doctor may administer a solution of hydrogen carbonate ions, HCO3-, intravenously to raise the pH to normal range. We can think of carbonic acid as an ionic compound that decomposes readily to aqueous hydrogen carbonate ions and hydrogen ions, which is H+. Administrating aqueous hydrogen carbonate will cause the equilibrium system in the equation above to shift away from the carbonic acid to the left toward the reactants. This reduces the acid concentration and so raises blood pH. Knowing how much hydrogen carbonate produces the desired shift can have life or death implications. Fortunately, the equilibrium law equation allows us to predict equilibrium shifts quantitatively. We know that the equilibrium constant doesn't change with concentration. However, adjusting any concentration of an entity in this expression will disturb the equilibrium. This will force the equilibrium to shift through changes in the concentration of other entities until the equilibrium constant is reestablished at its original value, which is indicating that the system is again at equilibrium. What happens at the level of the chemical entities to restore the equilibrium constant in a disturbed equilibrium? To answer this, imagine a reaction involving entities composed of two different hypothetical atoms, which we will represent as blue and purple circles. The chemical reaction between these entities is reversible, and the chemical reaction system has an equilibrium constant of 25. So we can represent this chemical reaction as follows. So as you see here, we have three of them plus these two is going to make it two blue, one, and the three of them with one purple. Now assume we place 12 of this compound and 12 this compound in a closed reaction chamber and allows them to react. Figure 2 depicts the entities in the reaction vessel before any chemical reactions have occurred. So suppose that we allow the chemical reaction to reach equilibrium. Since we know the values of the equilibrium constant is 25, the equilibrium law equation for this reaction can be represented graphically as below. We had this equation earlier for equilibrium constant, and then we can have them like that, before and after reaction, and count equilibrium entities, number of entities for each side. So as you see here, we have 12 of them initially, and the change is -5, and it produces 5 and 5 from the products. So eventually we have 7 here, 7 here, 5 here, and 5 here. So that's why it's going to be 5 times 5 divided by 7 times 7, which is 0.51. Since the calculated value using the numbers from table 1 is not 25, we know that our guess was incorrect. So the value that we calculated is less than 25, so we also know that the correct distribution must have a larger numerator, which is product relative to the denominator, which are reactants. Clearly, we underestimated by guessing that only 5 of the original reactants would need to react to reach equilibrium. How can we find the correct numbers? We might instead use a variable such as x to represent the number of entities that react and then analyze the distribution using I's table. That's what we had before. So we had 12 and 12 initially, and products we have 0 and 0, minus x, depending on the coefficient of the reactants. So if we assume they're 1, so we have just negative x, and if they are 1 as well, we have positive x. So then for E part, equilibrium part, we have 12 minus x, 0 plus x, which is positive x. So at the end, we have k equals to the product side, x times x, divided by the reactant side, 12 minus x times 12 minus x. So since we know that the equilibrium constant is 25, then we can solve it for x and then we can find x. So if we sub 25 here, so it's going to be x times x divided by 12 minus x times 12 minus x equals to 25. Then we have x squared divided by 12 minus x to the power of 2. Then we can find a square root of both sides. So then we have x over 12 minus x equals to plus minus 5. So the two scenarios, if we consider positive, x is going to be 10. If we consider negative, x is going to be 15. So we started with 12 entities of each reactant. So a value of 15 for x would give us a negative number of atoms, which is not possible. Therefore, the solution is that x is equal to 10 is our correct answer. So we accept the first one, we don't accept the second one. Therefore, the solution is that x equals to 10. And then to check that, we just sub 10 here. 10 times 10 divided by 2 times 2 is going to be, k is going to be 25. Now the next part, I want to talk about reaction quotient. The reaction quotient is the ratio of the product of the concentration of the products to the products of the concentration of the reactants. Like the equilibrium constant, the ratio can be used to analyze an equilibrium system. However, the reaction quotient can be calculated for a chemical reaction that is not at equilibrium condition. To obtain the reaction quotient, the equilibrium law equation is applied using instantaneous considerations. Instantaneous considerations are a set of considerations that correspond to a particular instant in time. The specific instant in time doesn't matter as long as the concentration of all reactants and products are measured at the same time. If the concentration of reactants and products are measured when a system is at equilibrium, then Q will be equal to K. So then reaction quotient Q will have the same value as equilibrium constant K. So when we are talking about reaction quotient, it means that we do the same thing, but it doesn't matter if it's equilibrium or not. And instead of equilibrium concentration, we have instantaneous concentration. So the reaction, the reaction quotient can be calculated for the chemical reaction that is not at equilibrium. And here we have reaction quotient, the product of the concentration of products divided by the product of concentration of the reactants for a chemical reaction that is not necessarily at equilibrium. Instantaneous concentration that occur together at a particular instant in time in the progress of a chemical reaction. It is often convenient to measure concentrations at the beginning of the reaction when all product concentrations are 0. For example, consider the synthesis of ammonia gas NH3 from gaseous nitrogen and hydrogen. You may recall that Fritz Haber's exploration of this reaction system won him the Nobel Prize in Chemistry. The balanced chemical equation for this reaction is N2 plus 3H2 equals to 2NH3. The reaction quotient equation for this reaction system at any time is NH3, the concentration NH3 or instantaneous concentration to the power of 2 divided by N2 to the power of 1 times H2 to the power of 3. When the concentration of any reactant or product is 0, the chemical equilibrium system will shift in the direction that produces the missing substance. What happens at the point when none of the concentrations are 0? To predict the direction in which the chemical equilibrium system will shift, we can compare the values of Q and the value of K. So what we learned here, when the concentration of any reactant or product is 0, the chemical equilibrium system will shift in the direction that produces the missing substance. It means that if the concentration of product is 0, the reaction will proceed toward the product side. If the concentration of reactant is 0, it means that the direction shifts to the reactant side. So now what happens at the point when none of them are 0? To predict the direction in which the chemical equilibrium system will shift, we can compare the values of K and Q. This part is very important. If Q, which is the reaction quotient, is less than K, the ratio of the concentration of products to the concentration of reactant is smaller than when the chemical system is at equilibrium. To move Q toward K, the concentration of product must increase while the concentration of reactants decrease. The chemical equilibrium system shifts to the right because the concentration has to increase for the product consuming reactant and forming products until equilibrium reaches. Second case, when Q equals to K. In this system, no shift will occur. The system will be at equilibrium and no shift will occur. And the third case is when Q is greater than K, the ratio of the concentration of products to the concentration of reactants is larger than when the chemical system is at equilibrium. To move Q toward K, the concentration of products must decrease and that of reactants must increase. The chemical equilibrium system shifts to the left, it means that shift to the reactant side, and converts products into reactants until it achieves equilibrium and Q equals to K. So that's what we have here. So let's review it in this figure. When K is greater than Q, system has too much reactant, so it shifts to the product side. A system at equilibrium, it means that Q and K are equal, so there is no shift. And the third case, when Q is greater than K, system has too much product, so it shifts to the reactant side. So now let's do this sample problem. Using Q to determine if a chemical reaction system is at equilibrium. For the synthesis of ammonia gas at 500 degrees Celsius in a closed vessel from gaseous nitrogen and hydrogen, the equilibrium constant K is 6.01 times 10 to the power of negative 2. The balanced chemical equation for this reaction is N2 plus 3H2 gives 2NH3. So for each of the following initial conditions, determine if the given concentrations represents an equilibrium. If not, predict the direction in which the reaction will proceed to reach equilibrium. So let's start with part A. The compounds concentration are given. So that's the initial concentration of ammonia, for example, nitrogen and hydrogen. So as you see here, we need to put it in this formula, Q equals to NH3 to the power of 2 based on this reaction, because that's balanced. NH3 to the power 2 divided by concentration of nitrogen times concentration of hydrogen to the power of 3. So then we sub all these concentrations there. 1 times 10 to the power of negative 3, 1 times 10 to the power of negative 5, and 2 times 10 to the power of negative 3. We sub everything there, and Q will be 1.25 times 10 to the power of 7. Then we compare it with the value of K. So as you see here, K is 6.01 times 10 to the power of negative 2. Q is greater than K, so the system is not at equilibrium. So let's see, where is it going to? Since Q is greater than K, the system has more of the product now than it would have at equilibrium. To reach equilibrium, the equilibrium system must shift to the left toward the reactants. So since Q is much greater than K, we have lots of products, and it has to shift to the reactant side, shift to the left hand side. That's the part A. Part B, we have the other sets of equilibrium, other sets of concentration. We just sub everything there. Q equals to, again, the same formula, NH3 to the power of 2 divided by concentration of nitrogen times concentration of hydrogen to the power of 3. So we sub all the numbers given here. So Q is 6.01 times 10 to the power of negative 2, and K is the same thing. So since K and Q are the same, we are at equilibrium. So since the chemical reaction system is at equilibrium at a given initial condition, it will not shift. And part C, there is another set of concentration. We sub it again in the formula and find Q equals to 2 times 10 to the power of negative 3, and Q is less than K, so the system is not at equilibrium, and to reach equilibrium, the equilibrium system must shift to the right side toward the products. Why? Because the concentration of reactants is much lower than what is supposed to be at equilibrium. So it shifts to the product side or to the right hand side in order to get to the equilibrium condition. So at the given initial conditions, the chemical equilibrium system will shift to the right toward the products to achieve equilibrium. These are the practice questions. Just pass this one. Now calculating equilibrium concentration. So calculating equilibrium concentrations. We can calculate the value of the equilibrium constant if we are given the initial concentration of all reactants and products and at least one equilibrium concentration. We can also calculate the equilibrium concentration from the equilibrium constant and the initial concentration. Sample problem 1. Determining equilibrium concentrations and K value from all initial concentration and one equilibrium concentration. So in this example, we have a reaction. Phosphorus pentachloride gas, PCl5, decomposes to form phosphorus trichloride, PCl3 gas, and chlorine gas, Cl2. A 2-liter sealed flask at 30 degrees Celsius initially contains 0.298 moles of phosphorus trichloride gas with the concentration of 8.7 times 10 to the power of negative 3 moles of phosphorus pentachloride gas and no chlorine gas. At equilibrium, the flask contains 2 times 10 to the power of negative 3 moles of chlorine gas. Calculate the equilibrium concentration of all entities and the value of K. So what is given? We have the volume, we have initial number of moles of PCl5, we have initial concentration of PCl3 and equilibrium concentration of Cl2. And there is no chlorine gas initially, so N of initial chlorine is 0. We need to find out the concentration of these two at equilibrium. So the volume is given. If we divide N by volume, we can find out the molar concentration. So if we find the initial concentration of PCl5, which is N divided by V, we have the number of moles, we divide it by volume to find out the molar concentration. We do the same thing for PCl3, the concentration And also we find out the equilibrium concentration for Cl2 by dividing it by volume. Then we construct the ice table. So these are the initial concentration. Chlorine is 0. Then we have changes, minus x plus x plus x, and we have so initially we have these three here, we have none of this, but we have the equilibrium concentration of chlorine. So the change from 0 to 1 times 10 to the power of negative 3 is the same number. So when this one is produced, it means that the same amount produced for PCl3 and same amount reduced from PCl5. So that's why we can find out the equilibrium concentration for PCl5 and PCl3. So 4.35 times 10 to the power of negative 3 minus 1 times 10 to the power of negative 3 is going to be the equilibrium concentration for PCl5. We do the same thing for PCl3, and we have this one as well. So K will be equal to Cl2 times PCl3 divided by PCl5. So this times this divided by PCl5 is gonna give us the K value, which is 4.48 times 10 to the power of negative 2. So statement, the equilibrium concentration of the reactant phosphorus pentachloride gas PCl5 is 3.35 times 10 to the power of minus 3 mole per liter. The equilibrium concentration of products are 0.15 for phosphorus trichloride gas and 1 times 10 to the power of negative 3 for PCl3 for chlorine gas. And the equilibrium constant for the equilibrium system is calculated here, which is 4.48 times 10 to the power of negative 2. Let's do another sample problem. So in this case we have carbon monoxide gas CO reacts with steam, which is H2O, to produce carbon dioxide CO2 and hydrogen at 700 Kelvin. The equilibrium constant is 5.10. So K is given. Calculate all equilibrium concentration if 1.25 mole of each entity is initially placed in 500 milliliter flask. So we need to write the equilibrium reaction, the reaction of carbon monoxide and steam. We have here CO plus H2O give us CO2 plus H2. The initial concentration of all of them are given, which are all of them is 1.25, and we need to divide it by the volume, which is in terms of milliliter, 500 milliliter. We need to convert it to liter, so we need to divide it by 1000, so it's going to be 0.5. So then we can say C equals to N divided by V. So we find the initial concentration for all the chemicals. So obviously all of them is going to be the same. All of them is going to be 2.5 mole per liter. So the initial concentration of all these four compounds are 2.5. So Q will be 2.5 times 2.5 divided by 2.5 times 2.5, as you see here, and Q will be equal to 1. If you compare it with K, K is 5.1, we can say Q is less than K. So since this Q is less than the given value of K, which is 5.10, the system is not at equilibrium. So for Q to be equal to K, the chemical reaction system must shift to the right, toward the products, to the products of this reaction to make it equilibrium condition. So then let's have an ice table. So we have initially 2.5, 2.5, 2.5, 2.5. The coefficient of all of them are 1, as in balanced chemical reaction. So if we have minus x here and plus x here. So we have 2.5 minus x, 2.5 minus x, 2.5 plus x, 2.5 plus x. And then we can put it in this equation for K value. K value is 5.10. The concentration of products in the numerator and the concentration of reactants in the denominator. So 2.5 plus x, 2.5 plus x is going to be on the numerator, and 2.5 minus x times 2.5 minus x in denominator. Then we can simplify, we can solve it. We can say 2.5 plus x, after finding the square root, 2.5 plus x divided by 2.5 minus x equals to plus minus 2.258. So we will end up having two answers for x values. What we need to do here, we just cross multiply, and the values for x is 0.965. So we just calculated for the positive one, so it's going to be 0.965, and the other one is going to be 6.475 when we use the negative one. So we have two numbers. Substituting this value of x into the expression for equilibrium concentration in ice table results in negative concentration values which are not possible in the real world. Therefore, use x equals to 9.65 in the equilibrium concentration calculations. So we didn't accept this one. Why? Because if we sub it in here, for example, this number, the equilibrium concentration will be negative. So this one is not acceptable at all, and we need to consider this one as x value. So since this one is x, we can sub it in here and we find the equilibrium concentration for all of them. So as you see here, the equilibrium concentration for COO and H2O are the same, which is 2.5 minus x, 2.5 minus 0.965, so it will be 1.535, and CO2 and H2 is 2.5 plus x, which is 2.5 plus 9.965, which is 3.465. So then we sub it here to check the value of equilibrium constant. So we have 3.465 times 3.465 divided by 1.535 times 1.535. That's gonna make it as close as 5.1. So we have 5.096. So the equilibrium concentration for both carbon monoxide gas and steam is 3.47 mole per liter. The equilibrium concentration for both carbon dioxide gas and hydrogen gas is 1.54. Now solving more complex equilibrium problems. So far we have worked only with problems in which the initial consideration and stoichiometry gave us polynomials that were easily reduced to simple linear equations. Considerations, temperatures, and equilibrium constants were carefully chosen so that you could follow the logic of the solutions more easily. However, in the real world, problem solving for chemical equilibrium will rarely involve linear equations. Instead, equilibrium problems often require working with higher order polynomials. In tutorial 3, you will see how and when to use the same strategy we have used thus far to solve these more complex problems. So let's see some examples. Sample problem 1. Carbon monoxide gas CO is the primary starting material in the synthesis of many organic compounds including methanol. At 2000 degrees Celsius, K is 6.4 times 10 to the power of negative 7 for the decomposition of carbon dioxide gas into carbon monoxide and oxygen. Calculate the concentration of all entities at equilibrium if 0.25 moles of CO2 is placed in a 1 liter closed container and heated to 2000 degrees Celsius. So we have the chemical reaction here. 2CO2 gives 2CO plus O2. That's balanced. And the initial concentration is given, which we have only CO2. The rest of them is 0. So the number of moles is given. We divide it by volume, which is 1. So C is going to be the same thing. So molar concentration is 0.25 mole per liter. So we need to find out the equilibrium concentration. So we have 2, 2, and 1 as the coefficients. So we have negative 2x because that's consuming. And on the product side, we have plus 2x and plus x. So 0.25 minus 2x gives you 2x and x in here. So k is going to be 2x to the power of 2, because the coefficient is 2, times x divided by 0.25 minus 2x to the power of 2. So as you see here, the exponents are 2 and 1 and 2. So in the numerator we have 2x to the power of 2 times x. So it's going to be 4x squared times x, which is 4x cubed, divided by 0.25 minus 2x to the power of 2 equals to the k value. And k value is given here, which is 6.4 times 10 to the power of negative 7. So then we need to solve this example. So we can say there is not an easy way to solve the cubic equation. However, you can simplify it by making some reasonable assumptions. Notice that the equilibrium constant value is very, very small compared to the initial concentration of carbon dioxide gas. So the equilibrium constant is very, very small. So from this you can assume that the value of x will also be so small as to be negligible. So if x is negligible, then 2x is negligible, and it's going to be a very small number. So we can say that CO2 at equilibrium, which is 0.25 minus 2x, and since x is very small number, 2x is going to be a very small number here, and we can consider it as a negligible or very insignificant number. So we can say approximately the concentration at equilibrium for CO2 is 0.25. So the denominator here is going to be just 0.25, and it's going to be much simpler than before. So it's going to be 0.25 to the power of 2. So then we have 4x cubed divided by 0.25 to the power of 2 equals to 6.4 times 10 to the power of negative 7. Cross multiplication, we have 4x cubed equals to the multiplication of these two. So x cubed is going to be 4 times 10 to the power of negative 8 divided by 4. And then x is going to be 2.15 times 10 to the power of negative 3. So now we need to use this value to test the validity of our earlier assumption. So when we sub it here, we had originally, before approximation, we had CO2 equilibrium equals to CO2 at initial minus 2x. Now we have the value of x, we sub it here, and as you see here, the value of the concentration didn't really change much. So the difference between 0.25 and 0.246 is just 0.004, which is only 1.6%. This very small discrepancy will have little effect on calculation of equilibrium concentration. In general, a difference of less than 5% justifies the simplifying assumption. It can be shown that if the concentration to which x is added or subtracted is at least 100 times the value of k, the simplifying assumption will give an error of less than 5%. We will call this the 100 rule. The 100 rule can determine if the simplifying assumption is warranted in a complex calculation, and so should be used before the calculation is made. So as you see here, we have 100 times bigger than k value, the initial concentration, so we can use this approximation method. So it's called 100 rules. So then we can say here we have the value, so the ratio is this one is greater than 100, so it was justified. So we can find out the equilibrium concentration for CO2, CO, and O2. We have all the equilibrium concentration. Then we can, based on that, find the K value. So if we go back to the reaction, we had 2 CO2 gives 2 CO plus O2. So we can say K equals to the concentration of CO to the power of 2 times O2 divided by CO2 to the power of 2. So we sub everything and then we find K value. The calculated is within 3% of the given value. So we tested and we checked that it's okay. So this part is extra is just for testing the answer. So the equilibrium concentration for gaseous carbon dioxide, carbon monoxide, and oxygen are 0.246, 4.3 times 10 to the power of negative 3 moles per liter, and 2.15 times 10 to the power of minus 3 moles per liter, respectively. Now let's do another example. Now rejecting an assumption about the magnitude of X. If 0.5 moles of dinitrogen tetroxide gas N2O4 is placed in a 1 liter closed container at 150 degrees Celsius, what will be the concentration of dinitrogen tetroxide gas and nitrogen dioxide gas NO2 at equilibrium? To equilibrium constant, the equilibrium constant is 4.5 under this condition. So we have the number of moles of N2O4, 0.5, and we have volume. So we find out the molar concentration, which will be the same, 0.5, and K is 4.5. So what we need to find? We need to find the concentration, equilibrium concentration for both. So we can have the ice table. N2O4 equals to 2 NO2. The initial concentration of N2O4 is 0.5, and the initial concentration of NO2 is 0. We have minus X, and here plus 2X. It is plus because it's producing, it is minus because it's decomposing, it's consuming. And the coefficient is 1, the coefficient is 2 here, so then we add them. We have 0.5 minus X, and here we have 0 plus 2X, so it's going to be just 2X. So then K is going to be NO2 to the power of 2 divided by concentration of N2O4. So we have NO2 to the power of 2 divided by N2O4 is going to be equal to 4.5 because the K value is given. So NO2 is 2X, so it's going to be 2X to the power of 2 divided by 0.5 minus X to the power of 1. So that's going to be the equation now. So we need to see if we can apply the 100 rule or not. So the initial concentration of N2O4 is 0.5 divided by K, which is 4.5, that's 0.111, and it's much less than 100. So the assumption that 0.5 plus X equals to 0.5 is not correct. So therefore we must solve the equation, and we cannot approximate it. So we have this one, we can use cross multiplication. So we have 2x to the power of 2 equals to 4.5 times 0.5 minus x. We expanded this one, and here we expanded this one too, 4x squared, and we simplify it. We have the quadratic equation, ax squared plus bx plus c. We can use quadratic formula. As you will see here, we have a is 4, b is 4.5, and c is negative 2.25. We sub everything there and we get two numbers, negative 1.5 and positive 0.375. So the negative, we cannot use it. That's not acceptable. Why? Because we cannot have it in here. So because, for example, it results to a negative equilibrium concentration for NO2. So we don't accept this one, we accept just the second one. So x will be equal to 0.375. Is the only acceptable solution to the quadratic equation. Use this value to calculate the equilibrium concentration for all of them. So we have 2x, which is 2 times 0.375, and here we have 0.5 minus 0.375. So these are going to be the equilibrium molar concentration for these two compounds. Check your result by calculating K to see if it's equal to the given value of 4.5, which is going to be 4.5. That's correct, and the solution is at equilibrium when the concentration of dinitrogen tetroxide is 0.125 mole per liter and the concentration of nitrogen dioxide is 0.75 mole per liter. Now problem number 3. So in this problem 3, we have rejected an assumption about the magnitude of X. Suppose that hydrogen fluoride gas HF is synthesized by combining 3 moles of hydrogen gas H2 and 6 moles of fluorine gas in a 3-liter sealed flask. Assume that the equilibrium constant for the synthesis reaction at this temperature is 1.15 times 10 to the power of 2. What are the concentration of each gas at equilibrium? So we write the equation. We have H2 plus F2 gives you 2HF. We have the initial concentration, initial number of moles, which is 3 and 6. We need to divide it by volume. So 3 divided by 3 for hydrogen gas is going to give you 1 mole per liter initial concentration. And initial concentration of fluorine, we have 6 divided by 3, we have 2 mole per liter. And there is no HF right from the beginning, so the number of moles is 0, so the concentration is 0 as well. So we need to find out the concentration at equilibrium. K is given, which is 1.15 times 10 to the power of 2. So we have the I stable. We have minus x because these are consuming and the coefficient is 1. And here the coefficient is 2 and it's producing, so we have positive 2x. So we have 1 minus x, 2 minus x, and here in this side we have 0 plus 2x, which is 2x. So K is going to be the concentration of HF to the power of 2 divided by concentration of F2 times concentration of H2, which is going to be 2x to the power of 2 divided by 1 minus x times 2 minus x. And it's going to be equal to 1.15 times 10 to the power of 2. Now compare the initial concentration of F2 by K. So the concentration is 2. If you divide it by K, it's going to be 0.017, which is much less than 100. So we cannot simplify it based on that assumption. So 2 minus x cannot be equals to 2. So we need to solve the quadratic equation. So we need to basically solve this equation. So we have 2x to the power of 2 divided by 1 minus x times 2 minus x equals to 1 times 15 times 10 to the power of 2. We cross multiply, we simplify it, and we end up having it like that, quadratic equation. X squared plus bx plus c. A is this number, b is this one, and c is this one. So we sub it there and we find two x values. One of them is 2.14 and the other one is 0.968. So let's see which one is acceptable. If we sub the value for 2.14 here, that doesn't look correct because that's gonna result in a negative number for the equilibrium concentration, so we cannot accept this one. So what we can accept is the second number, which is 0.968. So since the value of 2.14 for x would give a negative value for the equilibrium concentration of hydrogen gas, this value is not valid, so the correct value for x therefore is 0.968 mole per liter. Then we substitute it here, 1 minus x, 2 minus x, and 2x for all these three compounds, and then we find the equilibrium concentration. For example, for H2 we have 1 minus 0.968, which will give us 3.2 times 10 to the power of negative 2. For fluorine we have 2 minus 0.968, which is 1.03, and for HF we have 2 times x, which is 2 times 0.968, which is 1.94. So these are the equilibrium molar concentration. So if we want, we can check the values. We can just sub it back in the equilibrium constant formula to find out if the value of equilibrium constant is the same. So when you calculate it, it's going to be 1.14 times 10 to the power of 2, which is very close to 1.15 times 10 to the power of 2. So statement is the equilibrium concentration for this chemical reaction system are 3.2 times 10 to the power of negative 2 for hydrogen and 1.03 moles per liter for fluorine and 1.94 mole per liter for hydrogen fluoride. I hope you enjoyed this video. This is the end of this section. We have just practice question. So I hope you enjoyed this video. Please leave me a comment if you have any question and I'll get back to you as soon as possible. And please don't forget to subscribe this channel. Thank you.